This is chapter 6, problem number 37. The lucky number for this one is 9. Lucky number. Okay. There's a car, a 1,200 kilogram car moving on a horizontal surface, has speed v is equal to 85 kilometers per hour. When it strikes a horizontal coil spring and is brought to rest in a distance of 2.2 meters, what is the spring stiffness constant of the spring? Okay. Before anything, I would like to go over a few things. Okay. The first one is, for a spring, the force of a spring is equal to K times delta X, where K is the spring constant and F is the force. Okay. The potential energy of a spring is equal to half times K times delta X squared. Okay. We have also learned mechanical work is equal to force times distance. Okay. Kinetic energy is equal to half times mv squared. Another way of potential energy due to gravity, this one is S, due to a spring, due to gravity is equal to mgh. And now we have to use the concept of conservation of energy, try to solve this problem. Okay, so what is the problem about? Horizontally here, there's a car moving, okay? The car is kg, it's moving. And over here, there is a spring stretched out like this. Okay, it's not elongated, just a spring. So once the car moves in this direction and hit on the spring, guess what? The spring will be compressed. Okay, the spring will be compressed. So in this case, this will be my delta X. Okay. All right, so what happened is, over here, I have kinetic energy because it's moving. So when it compresses all the way to the end before it recoil and bounce back, okay, when it stopped over here, the kinetic energy will be equal to 0. Okay, so initially, kinetic energy is over here when the car is moving, and the potential energy due to a spring, it will be 0 because it did not compress or elongate. Over here, when the spring is compressed to the maximum, the car is stopped. So kinetic energy will be equal to 0. Okay, so if we set up the equation for conservation of energy, it will be potential energy plus kinetic energy. In the initial state, that will be equal to potential energy plus kinetic energy in the final state. Okay. All right, so what is the kinetic energy at the beginning? Well, the velocity is 85 kilometer. That means that many meter per hour. 1 hour I have 3600 seconds. Okay, so the first thing is I will convert the velocity into a standard unit. I don't like kilometers per hour. The standard unit will be meters per second. So I have 85000 divided by 3600. I have 23.6 meters per second. Okay, so initially I have half mv squared, that is kinetic energy, plus the potential energy of a spring, which is 0. At the end, I have the energy for a spring, the potential energy of a spring, plus the kinetic energy of the car, that is 0. Okay, so all the kinetic energy will be converted to potential energy of a spring. Okay. All right, so I'm going to plug in the number. Okay, it will be, I'm going to divide the half on both sides. So m is 1200 kilogram times velocity, that is 23.6 square. Make sure we put the square here. Last time I did not put the square. I forget, okay? But this time I remember. Well, during the calculation, I have to remember as well. That would be equal to times, spring constant K times delta X squared. That would be 2.2 meters squared, okay? Because it was compressed by 2.2 meters. All right, so we just have to solve for K. K is equal to 1200 times 23.6 square, okay? And then divided by 2.2 square. Okay, what I have, K is equal to 138,089 Newton per meter. Okay, or if you think it's too many numbers to write down, it's also equal to 138 kilonewton per meter. The lucky number for this problem is 9.